So today we're going to take a look at this rate of change that we saw yesterday and apply it in a more general sense. And that general sense is what we call in calculus the derivative. And the idea of the derivative is it has to do with this thing called the tangent line. And we saw a picture similar to this in yesterday's video, but just to kind of bring it back home again, let's say we're looking at some graph. Maybe this graph here. And what we're interested in is at some point x on the graph, actually, and what we're interested in is at some point x on the graph, we're going to compare it with some point down the line. So we're going to go down the line h units. We don't know how far that is. There's an x plus h point. So on the graph, that would be f of x. Or on the graph above the h, it would be f of x plus h. And if we were to connect these two with a line, it goes through the graph. When it goes through the graph, we call this a secant line. And what we found yesterday, to find the instantaneous rate of change, we would start shrinking h. So h would come up here. And that would give us a slightly different line that connects the points. Okay, that didn't quite connect the points, but you get the idea. And then we would make h a little bit smaller, and then we would look at the secant line that connects those 2 points, until we finally ended up with a line that does not go through the graph, but barely touches the graph at the point x. That line is called the tangent line. And that is that slope of the tangent line is what we're going to call the derivative. And just like before, we found the slope of this line by taking y2 minus y1, or f of x plus h, minus f of x, all over y2, which is x plus h, I'm sorry, x2, minus x1, which was just x. And then we made h shrink and shrink, so we were taking the limit as h went to 0. And just like before, the x minus x parts will subtract out to 0. And so we end up with this formula. The limit as h goes to 0 of f of x plus h minus f of x all over h. This formula is the slope of the tangent line. It is also called the derivative. This formula is going to be the big, important formula that we need to know for today, and really for a lot of the calculus that we're going to see coming up. The slope of the tangent line. So let's see if we can calculate some derivatives. Let's consider the function f of x equals 3x plus 2. And we're going to find the derivative of this first. Well, how about this? Let's first look at a secant line. We're going to find the slope of the secant between x equals 2 and x equals 3. So we want to find f of 2. That's 3 times 2 plus 2 which is 6 plus 2 is 8. In essence, we've got the point 2, 8. When 2 went in the function, 8 came out. And f of 3, well, sticking that in the function for the x, we've got 3 times 3 plus 2, which is 11. So when 3 goes in, 11 comes out. And so if we want the slope of the secant line, we've done slope a ton before. It's y2, 11 minus y1, 8 over x2, 3 minus x1, 2. And 11 minus 8, that's going to be 3. 3 minus 2, that's going to be 1. And 3 over 1 is equal to 3. This is the slope of the secant line between 2 and 3. Let's then, instead of looking for the secant line, let's find the slope of the tangent line. And here we're going to find the slope generally, and then we'll come back and actually calculate some points. So the slope is the limit as h goes to 0 of f of x plus h minus f of x all over h. So first f of x plus h, that means we're going to stick in for the x plus h. So it's 3 times x plus h plus 2. And then we subtract the entire f of x function, and we'll put that in parentheses, 3x plus 2 all over h. And don't forget, we want the limit as h goes to 0 of this. Doing a little simplifying, we'll distribute the 3, distribute the negative. When we do that, we get 3x plus 3h plus 2 minus 3x minus 2 all over h. You'll notice that 3x minus 3x is 0. Oops, what did I forget again? We need to have the limit as h goes to 0. Here we go. Then we have 2 minus 2 is 0. So what's left is the limit as h goes to 0 of 3h over h. And that's really nice because the h's divide out. And we have the limit as h goes to 0 of 3. Well, there's no h's in that to speak of. So the answer is just 3. The slope of the tangent line is 3. And because there's no variables in here, the slope of the tangent line is always going to be 3. Doesn't matter what x is, the slope of the tangent line is always going to be 3. So let's see if we can go to a little bit more interesting problem to play with. Let's do number 2. Let's consider this more interesting problem. Let's say f of x equals x squared plus 3. And we'll start out with the same thing. We are going to find the slope of the secant between, let's pick the same values again, x equals 2 and x equals 3. So we need to find what the values are at 2 and 3. So we'll do f of 2 is 2 squared plus 3. That's 4 plus 3 or 7. That means when 2 goes into the function, 7 comes out. And f of 3, that's going to be 3 squared plus 3. It's going to be 9 plus 3 or 12. So when 3 goes into the function, 12 comes out. And now we just need to calculate the slope between these 2 points for the secant line. slope. y2 is 12, minus y1 is 7, over y2 is 3, minus y1 is 2, 12 minus 7 is 5, 3 minus 2 is 1. So the slope of the secant line between 2 and 3 is 5. Let's find the slope then of the tangent line. The slope of the tangent line is the limit as h, the limit as h goes to 0 of f of x plus h minus f of x all over h. Whoops, scrolled too far, lost the function. So the function is stuff squared plus 3. First we're going to plug x plus h in for the stuff. X plus h squared plus 3 minus the entire function in parentheses x squared plus 3 all over h. So we want the limit as h goes to 0 of all of that stuff. So if we square the parentheses, we get x squared plus 2xh plus h squared plus 3. Distribute the negative, we get a minus x squared and a minus 3 all over h, and we want the limit as h goes to 0. Again, we can do a little bit of simplifying. The x squareds are going to subtract out. The 3's are going to subtract out. And so we're left with the limit as h goes to 0 of 2xh plus h squared all over h. This time we can't just reduce, because we can't reduce if there's any adding or subtracting in the numerator. What we do have to do is factor the numerator. And what we're specifically interested in, as the limit as h goes to 0, is if we can factor out an h so that it reduces with the denominator. That leaves 2x plus h all over h. And sure enough, those h's do divide out. So we have the limit as h goes to 0 of 2x plus h. And if we let h go all the way to 0, plug in a 0 in for h, we get 2x plus 0, which is just 2x. So the slope of the tangent line at any point is going to be 2 times whatever x is. So for example, earlier we were interested in the slope between 2 and 3. If we wanted to know the slope of the tangent line at x equals 2, that was the left side of the secant line, we just plug 2 in. So the slope is 2x, so 2 times 2 equals 4. 4 is the slope of the tangent line at x equals 2. We could find the slope of the tangent line at x equals 3, because we know the tangent line is 2x. So the tangent line is 2 times 3, or the tangent line here is 6. You notice the secant was somewhere in the middle. The secant had a slope of 5. But at the individual points, the slopes were 4 and 6. Now, it won't always work out that the slope of the secant is right in the middle of the slope of the tangents. But this time it did, just because of the nature of the function. We could even take this one step further. Let's say I want to find the entire equation of the tangent line at x equals 3. Well, remember, we already calculated the point of 3, going all the way to part A, at 3 we found the point was 3, 12. So let's use that. If we didn't know that already, we would have to calculate it. But we do know that 3, 12 is a point on the tangent line. We also just found out that the slope of the tangent line at 3 was 6. And so we'll remember that y equals mx plus b. Plugging in everything we know in here, y is 12, m is 6, x is 3, plus b. We don't know the y-intercept, but we'll find it quick enough, because 6 times 3 is 18. And when we subtract 18 from both sides, we get negative 6. So y equals m, the slope of 6, x, plus b, in this case, was negative 6. And this is the equation of the tangent line at the point x equals 3. Let's try calculating a few more derivatives. How about we find the derivative of f of x equals 1 over 2x plus 3. Remember, the derivative formula is the limit as h goes to 0 of f of x plus h minus f of x all over h. And so we're going to plug in for the x plus h. We have the limit as h goes to 0 of 1 over 2 times x plus h plus 3 minus the entire function, which is 1 over 2x plus 3 all over h. And now it's a big algebra problem. Let's see. Let's distribute through parentheses. That's going to give us the limit as h goes to 0 of 1 over 2x plus 2h plus 3 minus 1 over 2x plus 3 all over h. To subtract the fractions in the numerator, we need to have a common denominator. So let's do that. There's not going to be much we can do with the denominators other than keeping them like they are. So the first one we're going to multiply by 2x plus 3. And the second one we're going to multiply by 2x plus 2h plus 3. Top and bottom, that'll give us a common denominator. So we now have the limit as h goes to 0 of 2x plus 3 minus 1 times 2x plus 2h plus 3 all over a common denominator of 2x plus 2h plus 3 times 2x plus 3. And all of that is over h. Let's distribute that negative through. We have the limit as h goes to 0 of 2x plus 3 minus 2x minus 2h minus 3 all over the common denominator of 2x plus 2h plus 3 times 2x plus 3 all over h. Well, again, you'll notice the 2x subtracts out with the 2x. The 3 subtracts out with the 3. And so we're left with the limit as h goes to 0 of negative 2h over the common denominator of 2x plus 2h plus 3 times 2x plus 3 all over h. And what we like here, though, is we've got an h in the denominator and h in the numerator. Those h's can divide out. Another way to look at it is if we multiplied by the reciprocal 1 over h, the h's would divide out. So, same thing. Either way, what we have left is the limit as h goes to 0 of negative 2 over the common denominator of 2x plus 2h plus 3 times 2x plus 3. Now that we don't have just h in the bottom, now we can plug that 0 into the h. 2 times h, 2 times 0 goes away, so we have negative 2 over 2x plus 3 times 2x plus 3. Or maybe we can clean it up by writing negative 2 over 2x plus 3 squared. This is the derivative, the slope of the tangent line at any point x. I want to notice in this problem, the calculus part that we're doing was really, really simple. All the calculus is just using this formula, the limit as h goes to 0 of f of x plus h minus f of x minus h. And then after that, it's a whole lot of algebraic manipulation. Simplifying, combining terms, adding and subtracting fractions, reducing fractions. That's all algebra stuff that we did in Math 95, Math 99, and Math 141, and Math 120. We've done all that before. So let's try another one. Let's do f of x equals 3x squared minus 5x plus 2. Let's find the derivative of this guy, or the slope of the tangent line. The slope is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And this time you'll notice there's an x squared and a regular x. So when we do the limit as h goes to 0, we're going to have 3 times the stuff, which is x plus h squared, minus 5 times the stuff, which is x plus h plus 2. Then we subtract the entire function. So in parentheses, 3x squared minus 5x plus 2. All of that is over h. And now we start simplifying. Order of operations tells us that we have to do exponents first. So first we're going to square that x plus h. So we now have the limit as h goes to 0 of 3 times x squared plus 2xh plus h squared minus 5 times x plus h plus 2 minus 3x squared minus 5x plus 2 all over h. A little bit more algebraic simplifying. We're going to distribute through the parentheses, including the negative, all the way through. So we have the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 2 minus 3x squared plus 5x minus 2 all over h. Sometimes it has to get uglier before it gets better. A lot of algebra, easy calculus. 3x squared minus 3x squared, that's 0. Minus 5x plus 5x, that's 0. 2 minus 2, That's 0. So we have the limit as h goes to 0 of 6xh plus 3h squared minus 5h all over h. Okay. Now we're ready to start simplifying even more. Before we can reduce, we need to factor out an h. The limit as h goes to 0 of h times, we've got a 6x plus 3h minus 5 all over h. The h's finally reduce out, and we have the limit as h goes to 0 of 6x plus 3h minus 5. No more h's in the denominator, so now we're not undefined. Let's plug 0 in for h. That's 6x plus 3 times 0. That's 0 minus 5. The derivative of this function is 6x minus 5. Again, easy calculus, a lot of playing and massaging with our algebra skills to get it into a form that we can use, that we can plug 0 in for the h. Let's do one more. Let's do f of x equals the square root of 5x. Again, that formula, you're going to have it memorized by the end of the day. I want you to write it every time until you have it memorized. The limit as h goes to 0 of f of x plus h minus f of x all over h. With our function, we're plugging the x plus h into the x, so we have the limit as h goes to 0 of the square root of 5 times x plus h minus f of x, which is the square root of 5x, all over h. What are we going to do here? Well, let's do the easy thing first. Let's distribute the 5 into those parentheses. So we have the limit as h goes to 0 of the square root of 5x plus 5h minus the square root of 5x all over h. Problem here is we can't combine any like terms. The two square roots are separate from each other and they're not alike each other, so we can't combine those square root pieces together. We can't factor out an h to reduce with the denominator. So we're going to steal another trick that we have seen in algebra. You may recall, and this is just an aside, you may recall when we had functions like 3 over the square root of x plus 1. We didn't like that, so we rationalized the denominator by multiplying by the square root of x minus 1 on both sides, top and bottom. And that was nice because in the denominator, multiplying conjugates, the middle terms would subtract out to 0. We would have a positive square root of x and a negative square root of x, and they would subtract out to 0. So really, we only have to multiply square root of x times square root of x, which is x, and 1 times negative 1, which was negative 1. And the square roots are now gone out of the denominator because we did not want the square roots in the denominator. Very similar trick we're going to employ here is we do not want the square roots in the numerator because we can't combine the x's and the h's. So we're going to multiply by the conjugate and rationalize the numerator. That means we take exactly how it looks, just changing the sign in the middle. 5x plus 5h, and then we do a plus the square root of 5x Same thing in the denominator. Square root of 5x plus 5h plus the square root of 5x. When we do that, we get the limit as h goes to 0. In the numerator, we know because we're multiplying conjugates, the middle terms are going to subtract to 0. All we have to do is multiply the first term times the first term. And when a square root gets multiplied by itself, we just get the stuff inside, which is 5x plus 5h. And the last times the last, negative 5x over our denominator, which we don't have to multiply out, h times the square root of 5x plus 5h plus the square root of 5x. And now we're in business, because now the 5x's can subtract to 0. And we have the limit as h goes to 0 of 5h over h times the square root of 5x plus 5h plus the square root of 5x. And there we can do the thing we've been trying to do the whole time, is divide out that h, leaving us with the limit as h goes to 0 of 5 over the square root of 5x plus 5h plus the square root of 5x. The h is going to 0. Now that we don't have a factor of h in the denominator, we can replace the h with a 0, and we get 5 over the square root of 5x plus 0 plus the square root of 5x. And to clean it up a little bit, since we have two square roots, we're going to say 5 over 2 times the square root of 5x. We now have the derivative of our original function, the square root of 5x. So there's going to be a lot of algebra done today, and it's going to get even better as the course continues. The only new thing we're saying today is the derivative equation is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's how we calculate a derivative. Derivatives are going to be really important to us when we finally get into our applications of derivatives in Unit C, because we're going to start to think about graphs and graphs of derivatives and what they mean. So I want to do a little bit of graphing derivatives. We'll get to what they mean in the application in Unit C, but I just want to take a quick look at how we can graph the derivative of a function. Remember, when I say we're graphing the derivative of a function, we're graphing what's happening to the slope, or we're describing how the graph is changing. How the graph is changing. We're making a graph of the change of the original graph. And when we do that, it's going to be helpful to identify a few key things. Where is the slope 0? Because if the slope is 0, our y value is going to be 0. That's going to give us an x-intercept. We're also going to identify where is the slope increasing. If the slope is increasing, we have a positive slope, and so our derivative graph is going to be positive, showing an increasing slope. It's changing at a faster rate. And where is the slope decreasing? Or we have a negative slope, and that's going to put us in the negative portion of a graph. So let's try a really simple example. Really simple example. I'm going to do a parabola with a vertex over here at 2, 1. And then we are going to graph the derivative of the slope, the derivative of the graph. So first I want to know, where is the slope 0? Well, the slope is 0, the slope of the tangent line. Think about the tangent line. If this tangent line is going to touch this graph in only one spot and be completely flat, it's going to have to be right at the bottom. So that flat tangent line happens when x is equal to 2. So at x equals 2, the derivative is 0. So then we'll kind of split the graph into parts. On the left side of it, what type of slope do we have? Well, these tangent lines on the left side are all going down, right? Let's actually do those in a different color. If I draw a tangent line on the left of that 0 point, the left of that valley, you'll notice the slope is going down. These are negative slopes. Then on the right side, the slope is going up. These are positive slopes. So for our graph, we'll start negative on the left, getting steeper and steeper, and positive on the right, getting steeper or steeper. This is the derivative. So what we're kind of doing is drawing tangent lines on the graph to estimate the derivative. Noticing on my graph, as I get farther and farther to the right, my derivatives get steeper and steeper. So my derivative graph goes up and up. Let's try another one. But we'll try one that's a little more straightforward. Let's put a point here at -3, -2, a point at -1, 2, a point at 1, 2, a point at -1, at 2, -1, and then a point 3, -1. And I'm just going to draw straight lines connecting them. Okay. Remember, the derivative graph describes the slope of the tangent line. Notice this graph between, I'm going to split this into parts, between 0, I'm sorry, what is that? Between -3 and -1, what's the slope? You'll notice that it rises 2, runs 1. Rises 2, runs 1. The slope here is 2. Because the slope between -3 and -2 is 2, on my graph, between -3 and 2, between -3 and -1, between -3 and -1, I'm going to show that the slope is exactly 2. on my graph. Then the next part of the graph goes between -1 and 1. Let's do this in a different color. Between -1 and 1. So between -1 and 1, what's the slope of this piece? It's completely flat. It has a rise of 0 and a run of 2. The slope here is 0. It's completely flat. So we really should have open dots. Between -1 and 1, we're going to color the graph in, we're going to color the graph in at 0, because the slope between those points is 0. Next part of the graph is between 1 and 2. Between 1 and 2, what's the slope doing in that part? It goes down -1, -2, -3 over 1. -3, comma 1. It's going down, so we're going to do it -3 slope. The slope here is -3. And then again, for the last part of the graph, you see between 2 and 3, the slope is flat again. The slope there is 0. And so we end up with this graph for the derivative of our original function. Now, because this graph is all straight without any curves, our graphs are all flat without any bends for the derivative. Let's try another one. Let's try a graph that peaks up here at -2. We're going to have a point at 1. Notice the y values I don't care about so much. So it's going to come, we're going to go through -3, peak at -2, gradually come down to 1, valley at 2, and then come up at 3. And as we graph the tangent to this, what we care about is what is happening to the slope. First thing I look for is, where is the slope going to be 0? A 0 slope happens when the tangent line is flat. I don't know why it keeps trying to disappear on me. Tangent line is flat. Notice there's 2 points that we can draw a flat tangent line on. Those points are at -2 and at +2. Since you have a flat tangent line, the slope there is 0. And that's going to split the graph. These are not asymptotes. I'm just splitting the graph into parts. What's happening between those parts? Well, on the leftmost part, we've got some really steep tangent lines that suddenly get flatter and flatter as we get closer to our point. Are these tangent lines positive or negative? Well, because these tangent lines go uphill, they are going to be positive. So they're going to be really steep positive until they start to level out at 0. And then we've got these really shallow tangent lines. Shallow tangent lines, but notice these shallow tangent lines are going downhill. Downhill. So these go downhill until they start to get shallow again, at 0. This is kind of the y-coordinate we don't mind about much, but what I want to notice is it went shallow to steep, and then it started to come back to a 0 tangent line. And then afterwards, we start to get really steep, positive, uphill tangent lines again. And so we end up with this graph for our derivative graph. So the derivative graph describes the slopes of the tangent line. It tells us where the slopes of the tangent line are 0. If we're positive, the slope of the tangent line is positive. It's going uphill. It's increasing. Positive means we're increasing. The graph is going up, a positive slope. When the graph is negative, this is our decreasing. Negative slope. The slope is going down. Notice we were going downhill. When we go downhill, we see a negative slope. So we've got negative points on our graph. So really looking at the graph, how the graph behaves, what's the slope of the graph, we can generate a sketch, at least, of what we expect the derivative graph to look like. So we're doing two things today. We are finding derivatives using the formula. H goes to 0, the limit of f of x plus h minus f of x all over h. We are also finding graphs of derivatives. Take a look at it, your homework. Come back to class with questions, and we will see you then.